Okay, so yesterday we started the introduction to electron configurations. You're supposed to work through the first part of the POGL. You'll be doing the second part of it today to get some more of the definitions. But I kind of want to go over some of the stuff that we did yesterday to make sure that we're all on the same page. Good. Here we go. Before we go to electron configurations, real quick review on atomic structure. So you got Dalton's model, billiard balls. You got move on down the road to J.J. Thomson. We got the pick up the electron. Then Rutherford, we get the nuclear model. And then we get to Bohr, and the Bohr model is the one I told you the other day that I want you to kind of be thinking about, because the Bohr model has the nucleus in the middle, and then it's got the electrons in these orbitals going around the nucleus. The electron, the orbitals going around the nucleus. If we go to the modern atomic theory, is that we have a nucleus in the middle, but then we have these regions where the electrons are. It's kind of like we talked originally, it's like a beehive type thing. It still has the modern atomic theory, the quantum mechanic model still has the energy levels, but they're in what are literally called quantum, which are little packets of energy. And so it's a little bit difficult to ponder this notion, well, I've got this electron here and he can be here and he can be there, but the odds are he's in this region. It's from a big chemistry standpoint, it's more accurate, but for your understanding of how things work, the Bohr model is easier for you to understand, especially when we start thinking about electron configurations. Think of this as like a bowl, and the nucleus is here, and as electrons go into the bowl, they'll start filling at the bottom, the lowest energy, and then they'll go to the next energy level, and then they fill the next energy level. You can't have electrons up here until all these are filled. So every electron fills in a set pattern, and that pattern is the electron configuration, which is what we're picking up on. Some folks will find that electron configurations are a little bit confusing at first, but then as soon as it clicks, it'll be really, really easy. So if you'll pay attention to this, I'll be posting another video tomorrow. Once you look at both of those, and then I'll see you in person before you have to take a test on it. But if you once it starts clicking, just trust me, it's very, very easy, especially with that periodic table laid out in front of you. Here we go. We're going to be looking at using the Pauli exclusion principle. You'll learn the definition of that today. The Aufbau principle and Hund's rule to write electron configurations. And that's our learning objective. Electron configuration shows where the electrons are in an atom. It is a very set pattern. So once you learn the pattern, it always starts the same way. You just add electrons to it. So it's super, super easy. And the Aufbau principle says what I just said a second ago, that electrons always fill at the lowest energy and then work their way up. And again, you'll get that definition in your POGL today. I do not know what's going on here. It's going crazy. Okay. Let's talk about our house thing from yesterday. So you were looking at this house and you had the sunny rooms and you had the pink rooms, and the bottom floor of the house has a kitchen in it, so it's only got one room in it. The sunny rooms are analogous to orbitals, an s orbital, and the pink rooms go for p orbitals, and we're going to talk about those on the periodic table in just a few minutes. But what you should have picked up on, and hopefully you did by the end of the day yesterday, is you should have picked up that the rooms are the orbitals, the places where electrons can be, and the dots or the borders were the electrons. And each electron has to fill in a set pattern. So we start filling. First person obviously goes there, second person goes there, third person goes there, fourth person goes there, and then once we start filling the pink room, we fill them across the rows like this. So you wouldn't put the first person in this bunk bed and the second person up here. That would be weird. So if you go into the room and you got a bunk bed, you would take the next bunk, then the next bunk, then the next person has no choice but to go there. But the sunny rooms and the pink rooms are analogous to s orbitals and p orbitals, which again you'll be learning a little bit more about here in a minute. There are also other orbitals available. There are d orbitals, we'll talk about those in a little bit, which hold the s orbitals, hold 2 electrons, the p orbitals hold 6 electrons, the d orbitals hold 10, they're getting bigger and bigger. The further out you go, the more the room there are for electrons. And then the big guys, the f orbitals, will hold 14 electrons. And we're going to take a look at a picture of each of those here in just a second. You need to know the shapes of the s and the p. You don't have to know the shapes of the d and the f. So an s orbital is a sphere. S orbitals are always spherical. So we have a 1s, a 2s, a 3s, a 4s, a 5s, a 6s, and a 7s. They just get bigger and bigger and bigger and bigger and bigger. And when you look at the periodic table, again, I'm looking at the periodic table now, and I see the 1s, the 2s, the 3s, the 4s. And when we look at a periodic table, hydrogen's right there. This area right here is the S block. You'll notice the S block is 2 columns. That's hydrogen there, beryllium there, and again, you can get a periodic table. Look at these 2 columns are the S block, and there's 2 columns, 2 electrons. So it's 1s, 2s, 3s, 4s, 5s, 6s, 7s. And there are numbers down the side of your periodic table to help you get those. So S orbitals, you have to know the shape, spherical. The S orbitals on the periodic table are located in the first 2 columns. That's the S orbitals. S orbitals. Next guys up are the p orbitals. Now the p orbitals, this picture's a little bit, this picture's probably way accurate, but maybe a little bit hard for you to understand. Think of it like we have 3 axes, an X, a Y, and a Z in the plane, and the p orbitals are dumbbell shaped on each of the axes. They're dumbbell shaped in each of the axes. So you've got a P on the x-axis, a P on the z-axis, and a P on the y-axis. And each one of these can hold 2 electrons. So 2 electrons can go here, 2 electrons here, 2 electrons here, and 2 electrons here, which makes the p orbital able to hold a total of 6 electrons. 6 electrons. So we have the p orbital, and each of these represents a subshell of the p orbital. So you get 2 electrons, 2 electrons, 2 electrons. When you look at the hotel room thing, that's 3 bunk beds, 3 bunk beds, and keeping in mind that they fill, 1 will go here, first electron, 1 will go here, second electron, 1 will go here, third electron. Then when the 4th electron comes along, he goes back here again. 5th will go here, 6th will go here. On terms of the periodic table, we look at the general layout of the periodic table. Again, I'll put hydrogen there. There we got a block, and then we got a block here with this noble gases on the end. The element right here is boron to kind of get you oriented, and this is helium up here. Now helium is a weirdo, you got to keep in mind. Helium's sitting here because he's helium's sitting there because he's a noble gas, but in terms of electron configurations, helium should be sitting right here. And you will find some periodic tables online that put helium right there just because it matches with its electron configuration. But this area right here, this is what we call the P block. That's the P block. It starts with boron and slides all the way over to neon, and the P block has 6 columns because it holds 6 electrons. The columns represent the number of electrons. So the S block here, 2 columns. The P block here, 6 columns, because it'll hold 6 electrons. Again, remember, helium jumps over there. S block, P block, the most important 2 for you to know, the ones we'll run into the most often. The D block gets a little wonky, a little bit weird in the D block. But you can see S, P, next guy up is the D block. Now the D orbitals, you do not have to worry about the shapes. The D orbitals get a little bit crazy. You can Google those if you want to look at them a little bit. The D block, there are 5 sublevels, gives me a total of 10 electrons. If you were drawing a hotel version of that, you'd have 5 bunk beds. And again, they would fill person, 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 person. Before you ever put a person here, you got to get to number 6. On the periodic table, again, we got the hydrogen. There's our S block, little row here. There's our P block. There's helium right there, there's helium. This section right here, change color for me. This section right here is the D block, and it has 10 columns in it. 10 columns in it for the 10 electrons. The D block, 10 columns, 10 electrons. 10 columns, 10 electrons. A lot of weird stuff happens in the D block because it's so big and fuzzy. Most of that you don't have to worry about. Just be aware that sometimes the electron configurations don't follow the exact pattern, because it works out that, well, sometimes one of these that's supposed to be in the D block will jump over to a P block or fall back to an S block. I'll show you some examples of that before we take a test, but you won't be tested on those. That, again, that's an AP chemistry topic. But just be aware that because of the way the D block is so big and fuzzy, that some weird stuff happens with electron configurations in there. So S block, again, S block, first 2 columns. P block is this big block over here with helium belonging over there, and the D block are the guys right in the middle. D block guys right in the middle. The F block are the guys down at the very bottom, the lanthanides and the actinides. So you got the main periodic table up here. You got, these two guys down here are the F block. These two guys are the F block. There are a total of 14 electrons. You got to know the shape and the number of electrons in S and P. All you have to know about the D and the F is the number of electrons, and you can get that from the periodic table. Go to the D block, count the columns, you'll come up with 10. Now the problem is when you go to the F block and count the columns, depending on what periodic table you're using, you're not going to get 14. 14 is the right number, but if you count the columns, you might get 15. Because the periodic table, we always display it in these two pieces, but in reality, the periodic table looks like this. S block, the F block, the D block, and the P block. So the periodic table is supposed, that's a little high for that one. The periodic table is supposed to be really, really long, but since the F block guys don't show up that much, basically what they did was they snip, cut the periodic table off, shoved it together, and shoved the F block down at the bottom. But the F block may, depending on what periodic table you're using, it may have 15 columns because it takes these two right here, these two guys right here, and puts them at the very beginning. And so you end up with 15 columns. Just remember that the number of electrons in each orbital has got to be an even number, so when you count up 15, drop it back to 14, you're good to go. Okay, here we go. So you saw this yesterday. This is the energy orbital filling diagram. Lowest energy is the 1s, then it goes to the 2s. Notice that 2s and 2p are pretty close in energy compared to the 1s and 2s, but the 2p is a little bit higher energy, so the 2s has to fill first. 3s, 3p, 4s, but now if you look at 4s, look at this is where it starts getting a little bit wonky. At 4s, the 3d is actually it's actually lower energy than the 4p. So when they're filling in order, it goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and then look here, 4d, 5p, 6s. If the pattern gets a little bit hard to follow, you can look at it once you get used to it on the periodic table. Again, when we're in class, we'll walk through the whole thing on the periodic table so you can see them. And I've got a little shorthand notation thing I'm going to show you in a few minutes to help you get that going. But note that it starts out nice and easy. 1s, 2s, 2p, 3s, 3p, 4s. Then the pattern starts breaking apart because from 4s you'd expect to go to 4p, but you don't. You go to 3d. Again, don't try and just memorize the pattern because there's two ways to learn it. One is just using the periodic table directly, which I'll show you how to do that when we're in class. And two, I'm going to show you a little pattern here in just a moment. You can just go through them and learn all the orders. Here we go, 1s, there they go. Now when you take a look, you're going to say, wait a minute, whoa. What is this G's and H's and I's? Well, these are theoretical things. These guys over here, these G's and H's and I's, mathematically these gigantic orbitals exist. In reality, under normal conditions, they don't exist. At least they don't exist on Earth. They might exist like in the center of a sun or something of these gigantic atoms. But these guys are mathematically there, but they don't actually exist. But if you draw this out, 1s, 2s, 3s, 4s, 5s, 6s, 7s, 2p, 3p, 4p, 5, notice there is no 1p, there is no 1p, there is no 2d. These things do not exist. They're too close to the nucleus. P orbitals are too big to be way down here where the S's are. D orbitals are too big to be down here where the second energy level is. F's are too big to be at the third energy level where these are. So these do not exist just because they don't exist mathematically. These exist mathematically, but they don't exist in reality. So if you want to, when you're drawing this, just leave these guys off. You can just ignore them. But you need all the rest of them. Actually, I don't need a 7D either, but there we go. Okay, so when we start thinking about how the pattern goes, watch the arrows. You start at 1s, and then you keep going this diagonal pattern. 2s, and then 2p to 3s. Now notice it's going to keep following that pattern, so 3p to 4s. Who comes after 4s? Well, the pattern would show you it goes 4s, 3d, 4p, 5s. And then it keeps going at diagonals, right down through the diagonals. Right down through the diagonals. So what comes after 5d? Well, after 5d is 6p. After 6p is 7s. So if you write this out on a piece of paper, and you just put in the lines, and that's the end of the story, because these guys don't exist in the world that we live in. These guys don't exist under normal conditions. This picture right here, if you're going to do anything today from the video, you should freeze the video, get a picture of that, draw that on a piece of paper, get in the habit of, right, just go 1s, 2s, 3s, and then drawing these arrows. This is the order that they fill in. This is the order that they fill in. So what comes after 4f? 5d. What comes after 6p? 6s. What comes after 3p? 4s. You can just follow the pattern directly from the picture. The pattern is directly on the picture. The pattern is directly on the picture. So learn that. You need to be able to use that because you'll be having a test. For those of you that are in class, Thursday, Friday, you're going to have a test on Friday. We'll do a lab and some review stuff, and then we'll review a little bit, but then you have a test on Friday. So you got to make sure you can do this. When you look at the periodic table, S block, P block, D block, and the F block right down here. 1s, notice helium belongs right there. For helium belongs right there. And so when we start looking at electrons, it always goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. Notice I'm just following the periodic table by the numbers. 5s, 4d, 5p, 6s. Now you got to be careful here because these guys jump down here. 6s, 4f, 5d, 6p. Again, the pattern on the periodic table matches the pattern we saw in the picture just a second ago. Nothing's happening. Clicky, clicky. There we go. Okay, we're going to do an orbital notation and write an electron configuration for an element or two. So we're going to do nitrogen. So the orbital notation for nitrogen, first thing I need to do the electron configuration or orbital notation is look at the periodic table and see that it has 7 electrons. So when I do an orbital notation, I do a 1s, gets 2 electrons because it's full. Next guy on the list is 2s, he gets 2 electrons. Again, it's full. Nitrogen is a 2p, so it has 3 blanks for the 3 sublevels, and it gets, so I've already done 1, 2, 3, 4. I have 3 more electrons, so I go 1, 2, 3. So if I count up my arrows, 1, 2, 3, 4, 5, 6, 7, that is 7 electrons. That is the orbital notation for nitrogen. Do you have to do orbital notations? No, you won't be doing orbital notations on your test. I find, however, that orbital notations help students understand electron configurations because a rewrite of this would just be 1s, 2 electrons, 2 electrons. This, 2s, 2 electrons, and this, 2p, 3 electrons. Boom. That is the electron configuration for nitrogen. 1s2, 2s2, 2p3. In the 1s orbital, there's 2 electrons. In the 2s orbital, there's 2 electrons. In the 2p orbital, there's 3 electrons. Try aluminum. You try aluminum, just pause it, try aluminum, and once you pause it, you can start it up and I'll show you the answer for aluminum. Do the orbital filling diagram and the electron configuration. Okay, hopefully you paused it and gave it a try. So aluminum, first thing I always should ask myself is how many electrons? Well, there are 13 electrons, and everything always starts at 1s, so it's 1s, 2, 2s, 2. You'll notice I'm drawing an arrow up and then an arrow down to indicate different spins. So in an orbital, electrons spin clockwise or counterclockwise. They have to spin in opposite directions if they're in the same orbital. 2p it's full, so it says 1, 2, 3, 4, 5, 6. And then I jump to 3s, it's also full. And then 3p. Now the 3p for aluminum, I've already got 2, 4, 6, 8, 10, 12. I only need one more electron, so it's going to get one electron in it. It's going to kind of rub it in there a little bit. So the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p1. Boom. And if I count up the exponents, 2, 4, 10, 12, 13 equals the number of electrons, 13. The number of electrons equals the number, the exponent, the sum of the exponents equals the number of electrons. Now today, you're going to do the second part of the POGL that I started yesterday. Keep in mind one little thing about the grading. The Google Forms for short answers automatically gives you a 0 credit until I go in and grade it. So don't worry about those. If it's a short answer, if it's not a multiple choice, if it's a short answer, I have to manually grade those before your grade will update. So if you see a 0, don't send me an email and say, well, my answer was the right answer. I know, I just haven't graded it yet. So I'm grading every day. I'm putting stuff in every day. Can't think of anything else to tell you today. See some of y'all on Thursday, and look for another video to finish up electron configurations tomorrow. Thank you.